Good morning. Good morning. It's my great pleasure to welcome you to CVPR and also to welcome you to this tutorial on the mathematics of deep learning. My name is René Vidal. I'm a professor at Johns Hopkins University, and this tutorial is going to be given jointly with Raja Girgis from Tel Aviv University. So, as we all know, ever since 2012, deep learning has become mainstream in computer vision. And one of the major reasons has been the outstanding performance in a variety of visual recognition tasks. In particular, up until 2012, much of the object recognition methods were improving at a small rate, maybe a 1 or 2%. And in 2012, there was this dramatic 10% improvement by training a deep network on ImageNet and a network that had also a very large number of parameters. And the rest is history. So blue are methods not based on deep learning as of 2012. And that's what I meant, that the error in ImageNet used to be around 26%. And it went down to 15% in 2012 with AlexNet. But in 2013, the error went down again from 15 to 11. 2014, it went down from 12 to 6. And in 2015, it went down again to 3.5% with ResNet. So at the beginning, many people thought, well, this is only going to be the case for classification tasks, and it's only going to be the case when you have a huge amount of data, as you do in ImageNet, where you have a million examples. But certainly, people tried a few things. So they observed, for example, that if you fix the parameters of a network that is trained in ImageNet and you use it for other things, it actually works remarkably well. So what you can see on the top left is methods for just feeding the output of a network to a traditional SVM and then training it for a different task. So that's also the case of the second method. It was also applied to different domains, like recognition of faces with the deep face algorithm. So at some point, we sort of figure out, okay, it's probably going to work just for classification problems. And mysteriously, it has this property that you can use it in different data sets without much of a drop in performance. Something that was very unique, because many of us remember that methods from the 2000s, you would train in data set 1, you would test in data set 2, and you would always get a drop in performance of at least 10%. So we were proven wrong again. So it was extended to many other tasks, one of them being object detection. For example, by training the network with the output being now the bounding boxes so that you could localize where the objects are located. And it's been extended to almost any computer vision task at this point. So you can do pose estimation by training a network with the output being the pose of the object. Or you can do semantic segmentation. For example, there is the famous now segmentation net, where the output of the network is done via an encoding-decoding type of architecture. So once it's worked for almost everything you can possibly imagine, you can start thinking why this is the case. And so when you ask the practitioners and the experts in the topic, they would tell you one reason is that the features are learned rather than handcrafted. And therefore, that ought to have the effect that the features are more discriminative. They're more adapted to the task that you're interested in. And that's why it should be better. Another reason that it's given is that the more layers you add to the network, the more invariances you capture. So you want, of course, to do recognition with invariance to viewpoint, lighting, etc. And the example or the proof that is given is that you actually just do experiments. So the x-axis here is the number of layers. The y-axis is the mean average precision. And indeed, you do observe that the more layers you add, the better it works. And this is sort of very, very mysterious, because if you think about just training an SVM, for instance, by making the feature bigger and bigger and bigger, or adding more parameters to an SVM, you eventually expect that an SVM would suffer from overfitting. So it is sort of surprising here that you add more layers and you maybe don't necessarily suffer from the overfitting problem. The counter argument that is given is that we've got way more data, and as we will review briefly in a few moments, that doesn't seem to be a great explanation either, because if you go through the calculations from the 80s on how many training examples you would need to train, given the size of the network, you would need many more training examples than are actually used. So that's another surprising fact. Now, the other reason for the success that is given is, well, we can try lots of network architectures and we can feed them with very large data sets because we have a lot of better computing. Particularly, fortunately, the algorithm for training deep networks is very suitable to implementation in graphical processing units. But the other reason that people are starting to argue is, well, if you actually look at the networks from the 80s and you compare them with the networks of today, other than the fact that the networks are bigger and that the amount of data is more, what are the actual changes that have happened? And so one of them is that there is a different regularization strategy that is used. So back in the old times, for SVMs, for instance, we would regularize an SVM with the sum of the square of the weights. And so we would solve a loss plus regularization style problem. With dropout, instead, what you do is that you randomly select half of the weights and you don't update them. You only update 50% of them following a gradient descent or within the backpropagation strategy or stochastic gradient descent. So at the next step, what you do is that you randomly select another half of the weights. So why this strategy induces regularization formally, as usually done, and why that prevents from overfitting continues to be a mystery. The other change has been the type of nonlinearity. So back in the 80s, the nonlinearity that was preferred was this sigmoid that was meant to sort of resemble what the activation of a neuron does. It was replaced by this rectified linear unit that is 0 when the input is negative and the identity when the input is positive. So when you ask the experts why would this nonlinearity perform better, a typical answer that is given is that the sigmoid has gradient that is nearly 0 in most places. And so it's very hard, or it's very easy to get stuck and not move too much, while the rectified linear unit has a gradient that is equal to 1. And therefore, it's not going to get stuck. That's sort of the argument that's given. Now, if you give that argument to someone who does research in mathematical optimization, that mathematician will not be very satisfied by that answer, because whether the gradient is small or not shouldn't really be a reason to have guarantees of convergence, for example. It shouldn't be a reason to have guarantees of convergence to a good minimum, or it shouldn't have any guarantees of escaping a saddle point, for example. And so there has to be a better explanation for some of these phenomena. And last but not least, people have also observed experimentally that the number of weights sometimes is 0, or you end up with networks with a couple of weights that are different from 0. So I think it's fair to say that by and large, and with a few exceptions, the theoretical understanding of why deep networks work remains very shallow. So because neural networks are not a new thing, obviously people thought about some of these issues even 20 or 30 years ago. So one of the issues that people thought about is what kinds of functions are being approximated by a neural network. And a very outstanding result back from the late 80s was the fact that if you have a network just that has one hidden layer only, they are universal approximators. Namely, you can train them to approximate any function. And so when you start thinking about that, you're like, well, why do we need deep networks then? If with a shallow network with just one hidden layer we can approximate anything, then why do we need deeper networks? Now, how do we approximate everything though? We approximate everything by letting the number of neurons go to infinity. So in a sense, it's by having a very wide network. So obviously you would think, well, there is a trade-off between depth and width, and that's probably not very well understood. And people have even looked at it experimentally. If you train a shallow network with lots of neurons versus a deeper network, the deeper networks do work better. So why is it the case that deeper networks work better? So some recent explanations for some particular cases of networks have been provided. So there's been some connections made between deep networks and wavelets through the work of Stefan Mallat and Joan Bruna. And there's been this idea that if you ensure that at every layer you don't make the volume of the data grow, so in a sense the map from layer to layer is a contraction, then you can have guarantees of these networks effectively making the representations invariant to the formations. The second result that was back to 2003 is this question of generalization error in regularizers. So it was computed back then that the number of training examples that are needed in order to train a network grows exponentially with the network size. And that is a little bit what I was trying to argue, that if we look at the sizes of the databases today, and if we look at the sizes of the networks being trained, it does not make sense by the calculations made back in 2003. So either there is something wrong or something mysterious, or maybe the way in which the calculations were done back then was overly pessimistic. And more likely than so, there is extra structure in deep networks that allows the number of training examples needed to be much smaller. Okay? So this has indeed been investigated recently, and we will see today some results from Raja on the fact that if you've got networks with random weights, there is a notion of Gaussian width that allows you to capture properties of the network and allows you to tell things such as data from different classes, the distance from data points gets preserved, but data from the same class, the distance gets shrunk. And so that's a property that networks with Gaussian random weights have. And there's been also very interesting recent work on how networks should be regularized, and the fact that things such as sum of the square of the weights is perhaps not a good idea, and that you maybe need to consider all the paths that go from the input to the output and maybe take products of the norms of the weights as a better regularization strategy. And we will see that today as well. Regarding optimization, if we look at the literature in the late 80s and late 90s, the only case that people sort of were successful at showing that you could get globally optimal solutions was in the case of a linear neural network. So if you eliminate the nonlinearities, if you only have a single hidden layer, and if the data is separable, then things are good. Okay? But very easily, as soon as you add nonlinearities, people showed that backpropagation could get stuck in local minima. And so it wasn't until maybe 2005 that people started to observe a very interesting phenomena. And the phenomena was, and this was the paper from Benjo in 2005, that if the number of variables grows and grows and grows, eventually you get some sort of convexity. And I'm sort of hand-waving here a little bit. But the idea is that you can get convex neural networks if you have an infinite number of variables. This was done for networks with a single hidden layer. And the number of variables here is just the number of hidden units in that single hidden layer. In the last 3 years or so, there's been also very interesting work at making connections between neural networks with random Gaussian weights and certain phenomena that occurs in physics, particularly thin plate models, and trying to essentially look that in physics you always get the energy of a collection of particles, and you also want to find locations with that minimize that energy. And in physics there is a lot of phase transition phenomena, so if some parameter goes up, eventually maybe all local minima disappear. And so that phenomena has been sort of extrapolated to some classes of deep networks via simulation, and so people are starting to observe this phenomena that maybe the landscape is not so bad as we thought it was, maybe local minima disappear, and particularly so when the networks are large. So why this is the case? And we will see some of that today as well. So to summarize, the motivation of this tutorial is that deep networks have led to dramatic improvements in several tasks, but we don't necessarily understand the mathematical reasons for it. So the goal of this tutorial is to review recent progress at understanding 3 key properties of deep neural networks. One is optimization properties. Can we guarantee that the weights that are learned are globally optimal? The other one is going to be, what are the input-output properties of neural networks? Is it the case that we can have good metric learning properties with the input-output? And the last topic will be the topic of generalization. How can we measure the number of training examples that is needed to prevent overfitting? So by and large, there will not be a lot of results, so in terms of experiments. So the purpose of the tutorial is not to show again that it works very well on yet another example, but rather to understand the mathematical properties of it. So the rest of the schedule will be as follows. I'll begin with giving a talk about the topics of global optimality in deep learning. We'll have a coffee break from 10 to 10:30. And then from 10:30 onwards, there'll be 2 talks given by Raja. The first one is on the data structure-based theory for deep learning, this question of metric learning properties. And the second one will be about generalization bounds for guaranteeing that there is no overfitting. And we'll finish around 12 to 12:15 with questions and discussions. That being said, I think there are microphones in the middle, so if you have a question at any time or otherwise at the end of each presentation, we'll be happy to take questions. Right? So if there is any question at this point, while I transition, please raise your hand or go to the mic. Nope. Yes. Yes. So, yes. So the slides are on my website. If you go to my website and events, there is the list of all the tutorials. The slides for the CVPR 16 tutorials are already there. And the slides for this one, they're very similar, so I'll update them today, but you already have them available from last year. Okay, so let me begin with the first topic, which is the topic of global optimality in deep learning. So what is this question of optimization and why optimization is sort of a problem? So the key challenge in training neural networks is that the optimization problem is non-convex. So why is it the case that the optimization problem is non-convex? So suppose that I begin here with the features, and I'm denoting those features by V. You can think of that as being sort of the input data to the network here. And you can think of maybe the dimensions to be, you know, the number of rows in V might be the number of pixels. The number of columns might be, sorry, the other way around, is the number of training examples by the number of pixels in an image. Let's say it was that. So how does a deep network operate just mathematically? The first thing you do is that you apply some linear transformation to the data. The most common linear transformation is convolution, but it could potentially be a fully connected network, in whose case you are doing matrix multiplication. If it is convolution, then just think of the matrix. You know, convolution is a linear operation, so it can always be represented by matrix multiplication. So what you do next is to apply a nonlinearity. And as I mentioned earlier, it could be a sigmoid, it could be a rectified linear unit. And that gives you to the second layer. So now you repeat the process. You apply a second linear transformation and a second nonlinearity. And you do this capital K times if you have a network with K layers. What I want you to observe immediately is the following. I am going to introduce this notation phi to denote the output of the network. And the variables here, x1 through xk, are going to be the network weights. So x1 is the weights from the input layer to the first hidden layer, and so on and so forth. And notice that I'm not writing any dependency on the input v here. The reason being that I'm going to assume that the input is fixed. Okay? So you just gave me a training set, it is fixed, and I'm just trying to train the network for that fixed data set. Okay? So the output is a function, therefore, of the weights, because those are the variables from the perspective of optimization. Notice also that this map is a non-convex map. The reason being, even if you had no nonlinearity whatsoever, what is this map? It's just a chain of matrix multiplications. So it's x1, x2, x3, and so on and so forth. So already, even if you had only one hidden layer, you just have the multiplication of two matrices, in fact. So you immediately start thinking, aha, this seems to be related to matrix factorization, perhaps. So in fact, maybe it's very likely that learning the weight of a network, I can pose it as a factorization problem, where I give you the set of labels, and you factorize it into the weights of the first layer and the weights of the second layer. That is if you only had one hidden layer, of course. In reality, you have many, so it's like factorizing as product of many things, but in addition, you've got these nonlinearities on top that makes the fact that it's no longer a matrix factorization problem. So what problem is it then? Basically, what you do is that you're given a matrix of labels, y, so think of it as 0, 1, depending on whether data point I belongs to class J. And you would like to compare that matrix of labels with the output of the network according to some laws. The typical laws might be the sum of the squares of the prediction errors, or it could be the entropy laws, whichever your favorite laws might be. And then we put some regularization on the weights. In the 80s, that regularization would simply be sum of the squared of the entries of that weight. Today, often there is nothing. So the second term doesn't exist, and instead people do drop out, for example. So how do people handle the non-convexity today? So by and large, the method of choice for training deep networks is backpropagation. And today is done with stochastic, is a form of stochastic gradient descent, where you compute the gradient based on small batches of the data. But really, at the end of the day, really the technology is a particularly specialized form of gradient descent for doing the minimization. So because the problem is non-convex, in principle, you could get trapped in many local minima. So what is typically done to get a good minimizer is a little bit like trial and error. So either you know a good initialization for the weights to begin with, or otherwise what you do is you just look at the training error. If it is not going down very fast, it's very likely that it won't be a good solution, so you just throw it away. And you repeat this process from multiple initializations, and then you pick the best. A few mysteries have been observed. One of them is that you can get many potential minimas. What I tell joking sometimes is that if you give data to two different PhD students and you ask them to train the network, they'll come back to you with very different networks potentially, yet the classification performance will be about the same. What is this suggesting? It is suggesting that perhaps there are many local minima that are equal. Or maybe that there are many global minima, which by definition they have to be equal to each other. So if that was the case, this means that the non-convexity, what it really does is that it produces many global minimizers, and therefore, depending on where you start, you might converge to different ones. Also, but this changes depending on who you ask, but many people say that rectified linear units work better than sigmoids. And as I said earlier, the explanation given is that this phenomena of vanishing gradient associated with sigmoids. And the other phenomena is that you can find many units whose weights are identically equal to 0, particularly so for very large networks. Okay, so I already mentioned a little bit of the earlier work. So let me mention the key results that are known as of today at a very high level, a little bit hand-wavy, but hopefully it'll get the message across of what is known as of today. So suppose that you are trying to solve this training problem for a neural network. And as already said, is non-convex. So the following assumptions are made. Assumption number one, the loss function L, which is a function of two quantities, the labels, which are fixed, and the second argument is the output of the network. So as a function of the second argument, we're going to assume that the loss is convex. Okay? Is that a strong assumption? Well, not really, because what is the common loss that is being used today? For instance, sum of the squares of the errors, or the entropy loss, both of which are convex. Okay. The second assumption that we're going to make is that the loss is differentiable as a function of the output of the network. Is that a strong assumption? Not again. The sum of the square, the square loss is twice differentiable. In fact, it's strictly convex and twice differentiable, so it's even better than what this requires. And likewise, the entropy is also a differentiable function. Okay, so the first assumption is a very mild assumption. The second one, this might sound very weird to you, and so I'll spend a little bit of time explaining what it means. So we're going to assume that what is phi? Phi, again, is the output of the network. So it's written here. So it's the output of the network as a function of the network weights. We are going to assume that both that output as well as the regularizer are what is written here as positively homogeneous. What the hell does that mean? It means the following. Suppose that you scale the weights of the first layer by alpha. You scale the weights of the second layer by alpha. You scale the weights of the kth layer by alpha. So in the output, you look at the output, and that alpha actually comes out of the map and comes out raised to a certain power, p, okay? And that's what is called degree of homogeneity, okay? And the positively homogeneous is because we are going to assume that this is the case for non-negative scalings. All right, this seems like a very strange assumption. What does that mean? Is it actually satisfied by the neural networks that we're currently using? So let's go through a few examples. Let me take the rectified linear unit. The definition of the rectified linear unit is the maximum between the input and 0. If it is negative, it's set to 0. If it is positive, it stays the same. What if I scale that by alpha, right? Then the maximum will be scaled by alpha, provided that the alpha is non-negative. So a rectified linear unit has this property of homogeneity. If I scale the input weights, it scales the output, okay? And it scales by the factor alpha. So the degree of homogeneity is 1, okay? So in summary, a rectified linear unit is a positively homogeneous function of degree 1. I hope you start to appreciate why do I need positive? Because if the alpha was negative, which one takes the maximum would change. Instead of the maximum being still x, it would now be 0. And so the property will not be true. So the reason for the positive homogeneity is precisely in that case because you've got the maximum between x and 0. Second operation of our neural network, max pooling. In max pooling, what you do is that you take a neighborhood, you take a small patch, and you take the maximum response in that patch. So what happens if the weights are now scaled by alpha, right? Then the responses will be scaled by alpha, and the maximum value would also be scaled by alpha. So max pooling is another operation where it's positively homogeneous, and it's also positively homogeneous of degree 1, okay? And I need non-negativity again because I'm taking the maximum in a max pooling type operation. If any of the things was negative, then the maximum would change. So that's why we need non-negativity for the alpha. Okay. So what about a deep network right now? In the case of a deep network, let's say I scale by alpha the weights of the first layer, by alpha the weights of the second layer. What's going to happen? Well, what's going to happen is that I always have a linear transformation, right? Linear transformations, by definition, if I scale the input by alpha, the output is scaled by alpha. So linear transformations are also homogeneous. So what's happening at each layer is that I'm composing linear transformation with max pooling and with ReLUs, all of which are homogeneous of degree 1. So each layer is homogeneous of degree 1. And so if I just concatenate 2 layers, I'm going to get homogeneous of degree 2. If I concatenate k layers, I'm going to get homogeneous of degree k. Okay? So this is therefore a property that is already satisfied by existing networks. Not by all of them, right? If you do some sort of normalization, then everything changes. But at least networks where the nonlinearities are rectified linear units and max pooling, these properties are true. Okay, so the other assumption that we're going to make, let's go back to the assumption, is that both the network as well as the regularizer are homogeneous. Okay, let's think about what's your favorite regularizer again. Let's say that is L1. What happens if you scale the weights by alpha with L1? L1 gets scaled by alpha. So that's also homogeneous, right? What if you use L2 squared? If you scale the weights by alpha, what happens? Well, you get alpha squared. So that's homogeneous of degree 2. Okay? But look at what it says here. Look at the very last part. It says that they need to be homogeneous of the same degree. Aha. So if the network has k layers and has degree k, does it make sense to use a regularizer like L1? No, the degrees are not the same. So what this theory is predicting is that you need to use a regularizer whose degree matches the number of layers. So you should be using something like w to the k in order for this to work, as opposed to w squared. And so that might be an explanation as to why people have said, well, weight decay doesn't work so well. Because weight decay, usually they mean w squared, right? Okay. So under those assumptions, here is a first meta theorem at a very, very high level. It says that suppose that you pick your favorite algorithm for minimization. And suppose that you had an oracle that tells you, okay, you found the local minimum. If some entries of that x are equal to 0, and I'm being very vague as to which entries insofar, but if some entries are 0, that local minimum is a global minimum. Okay? In other words, giving you sort of a certificate to verify whether your local minimum is global. And all what you've got to do here is to check that some weights are equal to 0. Which weights? I'm going to be much more precise in a minute, but for the time being, just for you to have something in your head, think about a network with just one hidden layer. Suppose that all of the weights associated with one neuron were equal to 0. That's precisely what I mean here. So a network with a single hidden layer such that all of the weights for one neuron are 0, that local minimum is global. And effectively, what this theorem is giving you is sort of a measure of redundancy, because if one neuron has all the weights that are equal to 0, you can eliminate that neuron from the network without change. Okay? So that's sort of the intuition on the theorem that says that if the size is big enough, eventually some weights will be 0, and then you will know that you're a global minimum. The second theorem, which is slightly more practical, is that says the following. If the network size is big enough, what is the network size? Again, think about the number of neurons in a network with a single hidden layer. If the network size is big enough, then a local descent strategy, notice that I've written local descent and I'm being very vague here, but it's not just gradient descent. Okay? A local descent strategy will find that global minimizer from any initialization. This local descent is going to be a weird local descent strategy. Weird in the sense that typically we sort of like to have optimization problems, you know, there are 3 variables and it's fixed. I just minimize over 3 variables. In deep learning, okay, it might be 60 million, but it's 60 million, and I optimize over those 60 million. Here, the descent strategy is going to adapt the size of the network as you go along. So you might start with a network that is tiny, teeny, and the theorem 1 might not be true. So you might have no weights that are 0. So you increase the size. You add some more neurons. And then as you add more neurons, eventually the size will be big enough. and then you will get some weights that are 0, and then you know that you're at a global minimum. So by local descent, what is meant here is maybe a combination of descent, like gradient descent, plus this idea of adding or reducing the number of variables, effectively modifying the size and therefore providing a way to search a little bit for the architecture of the network. Okay, so pictorially, what this second theorem says is effectively the following. If I give you a generic non-convex function, the landscape could be fairly complex. So look at this region A here. That is a flat region. That is, it's maybe called a saddle plateau, right? Because it's not a maximum, it's not a minimum. B would be an isolated global minimizer. D would be a non-isolated global minimizer. And this picture is illustrating the fact that there could be many of them and that there could be an entire plateau of global minima. Of course, you could have local maxima and you can have local minima. That's in principle. So what this theorem 2 tells you is that if the size of the network is big enough, things such as h, right, that you need to increase the value of the function in order to escape, are guaranteed not to exist. So you might have a situation like this flat plateau, but notice I can traverse the plateau without increasing the value of the objective function. So I don't need to increase the value of the objective in order to escape those critical points. Okay. All right, so that's a very high-level explanation without getting into a lot of details. So now I'm going to zoom in a little bit into trying to explain why and what it means and where does this come from. And I'm going to do so by first just telling you about a very simple problem, which is matrix factorization. Because, as I hope I convinced you already, matrix factorization is a special case of deep learning where there is no nonlinearity and just one single hidden layer. So a linear network that's matrix factorization. Okay. And then I will explain how this extends to deep learning. Okay, so as it turns out, matrix factorization is an important problem in machine learning of its own, and it's got lots of applications from hyperspectral image. The Netflix challenge is one other example. And in computer vision also, if you think about subspaces for face recognition and face clustering, or motion segmentation, or structure for motion, cases where you've got subspaces appear all over the place, and matrix factorization is sort of the technique or the method of choice for many such problems. So matrix factorization, there are two types of approaches for solving them at a very, very high level. One is what I would call the convex type. And in the convex case, what you do is that you give me a matrix Y, and you want to approximate it by a matrix X according to some laws. And you have some regularization. Typically, you want that matrix to be low rank. And typically, if the loss is the square loss and you put the rank here, then you get PCA. So this is a very easy problem. So in general, if the regularizer is convex, this is a convex problem. The challenge is that the matrix can be really, really, really big for big data problems. And so that's why in many cases, people prefer the factorized formulation. If you know that that matrix is low rank, well, why don't you exploit that to begin with? So in that case, instead of solving for the product, X, one solves directly for the factors U and V. And so PCA, non-negative matrix factorization, sparse dictionary learning are all techniques that follow this paradigm. And the difference among them is what type of regularization do you put in the factors. For instance, if you want to do sparse dictionary learning, typically you want sparse coefficients. So you might put a sparse L1 penalty on the V matrix in here. The challenge is, however, that this problem is non-convex, and it's non-convex because that matrix multiplication that you put over there. Okay, so that's the source of non-convexity. So traditionally, people have said that non-negative matrix factorization is NP-hard, that there is no guarantees of global optimality. Sparse dictionary learning, there is lots of alternating minimization algorithms. In fact, almost a good number of papers in computer vision write down, the algorithm converges, and we verify that if you run it with 3 or 4 iterations, it works. But proving that that is the case for non-convex problems is actually very, very hard. Okay. So let me skip some of the examples. I think I've already given them. So what this slide is going to show, and maybe is the simplest technical slide in the sense that it gives you the gist of the results by just looking at them, is going to tell you why is it the case that you can have guarantees of global optimality for this non-convex matrix factorization problem. And the key insight really is that there's two versions of it go hand in hand. They're not equivalent, but they're so intimately related to each other that by exploiting the fact that there is a convex guy right next to me, I can have guarantees of global optimality for the non-convex. Specifically, how are these problems going to be addressed? We are going to exploit some result known as the variational form of the nuclear norm. What is that? First of all, what is the nuclear norm? The nuclear norm is, given a matrix X, is nothing but the sum of the singular values of that matrix, okay? And it's supposed to be a convex surrogate for the rank, because, you know, the rank is the number of non-zero singular values. So instead of counting how many are non-zero, you just sum them up, okay? And by doing so, you go from a non-convex quantity, like the rank, to a convex quantity, like the nuclear norm, okay? But as it turns out, you know, I've always said that why can we write things simply if we can make them more complex? We can write that thing in a very fancy way, and this is the fancy way we can write it. So on the right, suppose that you give me a matrix X, and my goal is to compute that nuclear norm, and I'm stubborn that I'm not going to just compute the singular values and add them up. I want to do something super fancy. What would I do? You give me X, and I tell you, find any factorization of X UV transpose. There could be many of them. I'm allowing the number of columns of U to be variable here. Among all possible factorizations, pick the one that minimizes this quantity. What is this quantity? Is the sum from 1 to R. R here is the number of columns of U. Okay? So it's sort of the size of the factorization of the norm of the ith column of U times the norm of the ith column of V. So in other words, it's sums of products of norms. That's what this regularizer is. And the magic is that if you minimize that over all matrices U and V, you get exactly the nuclear norm of X. Okay? Why am I going through this convoluted procedure? Because I'm going to pick that quantity, the sum of the product of norms, exactly as the regularizer for matrix multiplication. And now I'm going to ask you the question, are these two problems equivalent? Well, it appears so, right? It's like here I just did a substitution. Instead of X, I've got UV transpose. I just substituted. And instead of the nuclear norm, I substituted it by this. So that's what I put there. So maybe the two problems are equivalent, so if I have a global minimum for this, it'll be a global minimum for that. But not quite so because of this minimum that goes in here. So what is true is that this quantity is less than or equal than that, but they need not be equal. They're only equal if I minimize over all choices of U and V. Okay. Now, this thing can be generalized. Suppose that instead of putting the two norms in there, I put any norm. And in fact, in many problems, you want to put an L1. Or maybe in many computer vision problems, you want to put a total variation or any norm that you like. So this is what's meant here. Suppose that you pick any norm for U and any norm for V. It turns out that this variational thing generalizes and it gives some other norm that we're calling here the UV norm, and it's maybe not a great name. But the interesting thing, so this is the gist of everything and what I want you to stick in your mind. A convex function on the product is equal to the minimization of a non-convex thing on the factors. That's what this says, okay? And they're equal. So now with that, I write the theorem much more precisely in the case of matrix factorization. Suppose that you have to solve this non-convex problem. Given a matrix, factorizes as the product of U and V, but regularize with L1, L2, whatever your favorite regularization on the factors that you want. And this problem is non-convex, so in principle you do alternating minimization, whatever your method is, and you have no guarantees of optimality. So what this says is the following. Suppose that your algorithm found a local minimum. And suppose that that local minimum is such that one entire column of U and the corresponding column of V are identically equal to 0. Then that UV that you found is a global minimizer. Okay? In other words, in matrix factorization, a local minima such that one column is 0 is a global minimizer. Okay? Moreover, if you take the multiplication of that U and V that you obtained, that gives you a global minimum for the convex one. Okay? So the two problems are not equivalent, but they're intimately related. So the fact is that global minima of the convex and global minima of the non-convex are same, and in fact they're just related. The product of U and V gives you the global minima for X. Okay? That's the... And the proof for it, it's maybe long, but let me just write 2 bullet points here. The reason why this is true is because of this intimate connection between the non-convex problem that I want to solve and a convex problem that is right next to it. And in fact, that convex problem is a global lower bound. And it's a global lower bound because I just said the first term, the last term is equal because it's just substitution. The second term is the lower bound because the fancy norm on X is the minimum of that sum of products thing. Okay? Pictorially, what this theorem says is simply that the local minimizer you found is sort of redundant. It's kind of almost like saying, you know, I've got a low rank matrix, but I don't know the size, and I'm going to overestimate the size. So eventually, you do know that if you set some columns to 0, then you can reduce the size of your factorization and still factorize that matrix perfectly. So the certificate for global optimality is exactly saying that you've put too many columns and one of them is 0. The second theorem is this theorem that says that if the size is big enough, again, what is size here? The size is just the size of the factorization, the number of columns of the matrix. If the size is big enough, then you can reach the global minimizer from any initialization. How? How do you do so? So look at this picture here. Suppose that I start here, and suppose that I start with whatever, with some size for my factorization. So I do gradient descent if you want, or I do maybe alternating minimization, or I do proximal gradient, whatever your favorite method is. And I go down, 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 down. And so eventually I'm going to arrive here at a local minimizer. Okay? So what we're going to do is ask this question here. Are you at a local minimum? Yeah, if you're not a local minimum, you know, keep going down. If you are at a local minimum, then test if theorem 1 is satisfied. Namely, test if one column is equal to 0. If that's the case, then you're done. You found the global minimizer. Obviously, I'm here, so that's not the case. So what we're going to do is that we're going to increase the size of the factorization by 1. So we're going to add 1 column to U. We're going to add 1 column to V. And we're going to select that U and V in a very peculiar way so that I guarantee that I keep going down. Mathematically, or pictorially rather, this is really like traversing this flat plateau from the left to the right in just one step by adding that extra column. And so now I move from the left to the right by increasing the size, and then I keep going down, and eventually I'll get to that global minimum. Now, this is sort of a meta algorithm. It's not necessarily implementable, and there are 2 things that are hidden under the rug and that require further research. First, can you guarantee that you are at a local minimum for a non-convex problem? Not very often, right? The question of just guaranteeing that you're a local minimum is usually NP hard for many optimization problems. So whether that is the case and for what classes of neural networks is the case, that's still an open question that is heavily being investigated as we speak. Second, suppose that actually for the neural network you're training, you had a optimization method that would guarantee you are at local minimum. Then you have this question of, can I increase the size, and how do I select a descent direction? For some regularizers, that question is trivial. For the L2 that I was just talking about before, you have to solve an eigenvalue problem, and with that you choose the U and the V. But in general, that question is also NP hard, depending on what regularizer you pick. So developing or figuring out for what regularizations you can, the problem of augmenting the size of the network is tractable. It's another open challenge. Let me check the time. Okay, so let me now move on to how this extends to deep networks. So I hope I've convinced you so far that matrix factorization is a special case of deep learning with no nonlinearities and just one hidden layer, and that for matrix factorization you can guarantee global optimality. And how did I convince you of that? I said, well, the problem is non-convex, but there is a very strongly related problem that is convex, and the two are so related that you can use one to guarantee the global optimality of the other. That was sort of the high-level message. What types of neural networks can this be extended to? So the first one is nearly immediate, is neural networks with a single hidden layer. In this particular case, it's almost like matrix factorization. So these are the weights from the input layer to the mid layer, and the weights now from the mid layer to the output layer. If there is no nonlinearity, this is just matrix factorization. So the number of columns of that matrix now becomes the number of neurons of that hidden layer. Okay? The second type of architecture for which this framework applies is the one that is illustrated here. Suppose that you've got whatever your favorite deep network is with as many layers as you want, as many neurons per layer. The only requirements are those that I stated at the beginning, that the functions need to be positively homogeneous. So rectified linear units is good, max pooling is good, but other things might not be. So what you're going to do now is replicate that network multiple times. So now you put many networks in parallel, and then you sum in order to generate the output. Okay? So in this particular case, what is the definition of size? The size is going to be the number of parallel subnetworks. Okay? So here size is the number of hidden units. Here size is the number of parallel subnetworks. The reason being that the theorems so far are restrictive in the fact that there is just one number characterizing size, or effectively it's like what is the complexity of this architecture. So for matrix factorization, it's sort of very clear, is the number of columns that you put in that factorization. But for deep networks, it's not as trivial, because you could say, well, it's the number of layers, or is the number of neurons. What is it? So this is a little bit of a contrived example where the number of layers and neurons is fixed to whatever you want for your architecture. And size, which is the only thing you can vary, is just the number of parallel subnetworks. So this is the generalized factorization problem. And matrix factorization, as I've said repeatedly, is a particular case. And I've said that both are positively homogeneous, which is sort of the requirement for the theorems. Okay. So this is the first thing we need to extend. How do we extend the concept of matrix multiplication to multiple layers with nonlinearities? So the way we're going to extend it is, think about the matrix factorization here. It's UV transpose, but you can always write it as sum from 1 to the size of outer product of the columns of the matrices. So that's all we need to do, really, and this is the more general formula. The output of the network depends on many layers and many weights, and they could be matrices or tensors, whatever they are. But we are going to write it sum from 1 to the size of the network, where size, I already explained what I meant, of positively homogeneous functions of those weights. Okay, that's the key insight. And I hope that this gives you an example. For matrix factorization, the sum is running over the size, and the positively homogeneous function is just outer product of the columns. Okay? So in the case of a 3-layer neural network, this is the input-output map, and it satisfies the properties that I just said. So in fact, look at it. Input data multiplied by the matrix of weights, nonlinearity multiplied by now the classifiers. So this is almost like matrix factorization. The only difference between a neural network with a single hidden layer and matrix factorization is that nonlinear map that you put in the middle. Okay. Okay, so the next and the key thing that I need to tell you is how do I generalize the regularizer. So the regularizer for matrix factorization came from that variational form of the nuclear norm. And what was it? It was sum of products of norms. That's what it was. Okay? And there was this beautiful property that the fancy norm of a matrix is obtained by find a factorization of it, and among all possible factorizations, minimize the sum of the products. So now is how in the world are we going to generalize that to deep networks? So here is the generalization. I'm going to start with the far right, so look at where my mouse is. So pick the output X of the network, right? Select the weights X1 through Xk such that the network produces X as its output. So this is entirely equivalent to this. Given a matrix X, find a factorization of it. Similarly here, given the output of a network, find the weights that produce that output. Any choice will do, and the choice is not unique, and there might be many of them, in the same way that there are many factorizations here. Among all possible choices of weights that generate that X, select those that minimize something like that, sums of products of weights. So in particular, or more generally, any positively homogeneous function of those weights will do the job. Okay? And the minimum of that is a function of X, in the same way that the minimum of this was some function of X. Here, this was a norm, and it was convex, and that's what gave me the convex problem. Now, what is this omega of X? And so here is the fundamental result, that in spite of this being fancy and having lots of products, and it gives you a function that is convex. Okay? It produces a function that is convex on the output of the network. So even though we're going to have a non-convex problem on the weights, we will find a problem that is convex on the output. And so this is now the main theorem stated with more proper notation. The training problem for a deep network is minimize the loss between the labels and the output of the network plus lambda times some regularization on the weights. That problem is quote unquote, because it's not, but it's equivalent to minimizing the loss between the labels and some output of the network with some regularizer on the output. And as it turns out, that regularizer is convex. So if the loss is convex on the output, then you've got a convex problem to work with. And these two are not equivalent, but they're strongly related. And as I said earlier, the convex problem is a global lower bound for the non-convex. And particular cases are matrix factorization. And so what this theorem says, again, is if you find a local minimizer of this neural network training problem, such that some of the weights of that network are zero. Which ones? All of the weights associated with one neuron for the case of a network with a single layer. Or all of the weights of one parallel subnetwork in the other example where there were many parallel subnetworks. So if all of the weights or all of those, if a collection of weights is equal to zero, then that local minimizer is global. Moreover, phi of those weights is also a global minimizer for this convex problem. Okay. And again, this suggests sort of a meta-algorithm for optimizing both over the architecture of a network as well as over the weights. And the algorithm is essentially the following. Start with a network of fixed size. Let me actually just illustrate it with network with a single hidden layer. Suppose that I start with a network with 5 neurons in the mid layer, just say. I minimize over those 5 weights, or whatever the number of weights is, and I find a local minimum. I check, are the weights associated with a single neuron equal to 0? No. Therefore, you need to add an extra neuron, initialize the weights for that extra neuron in a clever way, and now continue with your back propagation again for a new network that has 1 extra neuron. You keep repeating this process of minimize, add an extra neuron, up until eventually all of the weights associated with 1 neuron are going to be equal to 0. When that happens, you know that you are at the global minimum. So to summarize, there are 3 big messages of this first lecture. The first one is that size matters. Namely, one reason why we might be stuck with loss of local minima is because we tend to optimize over things with fixed size. When we do matrix factorization, we tend to fix the number of columns. And the message is that if the size you pick is too small, then there will be many local minima. But if the size you pick is very large, eventually those local minima will disappear. So today, I've covered very simple cases, like adding 1 neuron at a time for a neural network with a single hidden layer. What we would like to do in the future, and we don't quite know how to do yet, is how do you jointly add new layers and add more neurons to the layers? More broadly, how do you optimize over the architecture? Because I think it's fair to say that, it's true, we've gone from handcrafted features to learned features. But I think the reality is that we've gone from handcrafted features to handcrafted architectures. And therefore, in the future, having a methodology that will optimize over what the architecture should be is very important. And I think this framework provides the tip of the iceberg by just telling you how do you optimize when you just have to add 1 neuron at a time. The second message of this lecture is that regularization matters. And in particular, these sums of positively homogeneous type of regularizers is what shows up. And more importantly, the degree of the regularizer has to match the degree of the network. So we should be using degree k, for instance, for a network with k layers. Now, how to build more sophisticated regularizers that are able to capture many layers and so, that's open problem from the perspective of optimization, but you will see from Raja's talk actually how to build regularizers with good generalization performance in a moment. Now, these results are very preliminary and just the tip of the iceberg because there are 2 bad things about them, or maybe 3. One is that I've always said many times, if the size is big enough, everything is nice. But how big enough is big enough? And so the results today, that big number is too big to be practical. Typically is for a neural network, the size of the neural network would need to be the dimension of the input times the dimension of the output. So if it was images, it would be number of pixels by number of classes. So that size is perhaps too big. In matrix factorization in particular, you know that that number is way too big, because if I'm trying to factorize a matrix that is m by n, the rank is way smaller than m times n. So there is a lot of hope that that size criteria can be made better, but not as of today. And the other aspect is that much of the results are just sort of meta-algorithm-like, so verifying that you're at local minima, hard problem of its own. Adding an extra column so that it's at the same direction, also another hard problem of its own. Thank you, and I'm ready for questions. There's a mic there.
Hi. So just a quick technical question. When you have a matrix X, how do you know that there exist this sort of deep decompositions? For matrix factorization, we know, but for when you have the nonlinearities, how do you know that there exists a decomposition?
The composition, I mean, the fact that outputs of the networks do exist is by construction, because
Yes,
you have
of
an
course,
input
but,
and you produce. Given matrix X, does it exist? You don't know, because the output might only generate a subset of the space. That being said, you are searching the X. The X is just a fictitious quantity, because you're not optimizing over it. You're always optimizing over the weights. So that X always exists by construction as you're proceeding through the iterations.
But doesn't it break the convexity of the relaxation of the which is about X? Because then you have a constraint that X has to live. If you take the relaxed problem, X has to live in some image of your network, which may be a non-convex set, is it?
Yes, but again, it is not that we are asserting that the two problems are equivalent. We are asserting that the global minimum are the same. And therefore, it's not needed exactly that you impose those constraints in X.
Okay, thank you.
So it's really interesting work. So I'm just wondering, so in the context of your study, how do you think about the function of a dropout, since like the dropout as a regularization?
Yes. This is unpublished work that one of my students has been working on, and it's very long to explain, so let me try to do it in 30 seconds. If you apply dropout to matrix factorization by dropping out a certain factor, right? And if you think of that dropout as a Bernoulli random variable, and now you consider the loss, so the loss now is evaluated with a random quantity. Suppose you take the expected value of the loss with respect to the choice of the Bernoulli variables. You can prove analytically that that gives you a loss on the factorization plus a regularizer. And you can prove that that regularizer is the sum of the product of the norms of the columns of the matrix. With the exception is that it's squared, so modulo that hand-waving part. What I conjecture is that dropout is inducing a form of regularization that is precisely sum of products of weights, and that by studying it further, we are going to be, and that dropout is a stochastic gradient descent approach for minimizing that loss, and therefore that you can have guarantees of global optimality because of the type of regularization that is induced, which exactly follows within this family that I discussed today. But it's a work in progress.
Okay. Yeah. Thank you. So follow up. So in that sense, so does it fit also the assumption of that the positively homogeneous has to be at the same degree for the dropout?
No, in dropout it doesn't. In fact, you get the squared. And so the degree of the regularizer is twice as much. So we had to actually correct the dropout rate in a way that it increases with the size of the factorization. So the dropout rate is not, as the larger the matrix, the more you have to drop out kind of thing, in order to redo the results for global optimality. So it doesn't follow directly. It needs a little bit of adaptation.
Okay, thank you.
Yes? Yes. Yes. Yeah. Yes. Yeah. Yes. So maybe I was not clear enough, but we are solving the problems in the factorized space, not in the X space. And so we are never solving the convex problem in a large number of variables. Yeah. I mean, if the matrix to be factorized is of the size of an image and you have thousands of images, you can't even do it with SDP programming. And you can do it with these methods. So I don't have precise numbers of the speedup that you get, but it's very clear that you cannot use the SDP for very large data.